Let's start with an overview of the library. Well, we need to look at why did we do this research. Well, simulation for X-ray attenuation has been extensively studied in physics, and there are plenty of code available, and usually they are based on Monte Carlo methods, and very often on CPUs, but now we can see a lot of implementation using graphics card, and they're often aimed at dosimetry for radiotherapy. So this type of code is very accurate. However, computing an image may require a long time. And some of the images I used for validation took a week of computation. So we know that ray tracing is an alternative. Well, it might still be slow on the CPU. Also, we see this is what we try to accelerate. With ray tracing, it's not easy to take into account scattering. However, is it really needed? For many X-ray transmission imaging, we don't necessarily care much about scattering. And in that case, maybe we can just ignore it. By definition, ray tracing does not include Poisson noise. But that can be added as a post-process. I started my PhD in 2003, and then I did a postdoc in 2006, and both were aimed at medical virtual reality. And we were developing programs to train interventional radiologists. And basically what they do is to stick needles or catheters in the human body. And when they do that, they don't look at the patient, they look at a screen. And the screen may be showing fluoroscopy, which is a real-time X-ray image. And in that case, as I said previously, we are not interested in scattering, and noise is not an issue. And in that context, ray tracing is a viable option. So we did some bibliography study, and well, we came up with the conclusion that we needed a library that we could use, so hopefully open source, but with flexible license, because we are looking at a commercial prototype. So the license should allow that. It should be fast because training simulator must run in real time, so we were looking at GPU implementation. And cross-platform, well, because why not? And I decided that it should be validated so that we are sure that the images are accurate. So, in a nutshell, gVirtualXRay is a C++ X-ray simulation library. It's open source, it works in real time, it's portable, validated, and available for many programming languages. So it's hosted on SourceForge, so anyone can download the code. There are also some release. It's implemented using C++ and OpenGL. It works on Linux, Windows, and Mac OS. And it's been tested on various graphics cards from NVIDIA and AMD. And I know it also works with integrated GPUs. And it's been tested on desktop PCs and laptops. So we've done some quantitative validation that we will see later on. And because this is using ray tracing, we can reproduce the results. So something you do on one computer will be the same on another computer. We are using XCOM photo cross-section database from NIST. So this is not necessarily an issue, but you have to know that I can't provide these data files, so they are downloaded even automatically during the install, but I can't provide them myself because they are not mine. So they are downloaded directly from the NIST website. And that allows us to have a very accurate physical model. The input data are 3D meshes. So we're supporting plenty of file formats, STL, PLY, 3ds, etc., etc. And that's done via the ASIM library. So in terms of simulation, well, we can have various shapes for the source. It could be a point, just a tiny point. It could be a parallel beam, like what we will simulate maybe from a synchrotron. And it could be a cube, or so that we could actually simulate the actual size of the X-ray tube. The beam could be monochromatic, so there's only one energy in the beam, or polychromatic with several energies in the beam. And to do that, we can just use CSV files. Geometries, where the objects that we image could be surface meshes, like triangle meshes, or volume meshes made from tetrahedron. So this is something relatively new compared to 2 years ago when I presented this library. Material properties. So 2 years ago, we could only support chemical elements, like tungsten, for example, or Hounsfield unit, but that's for medical application. So today, we can now simulate compound, like water, H2O, or mixtures, like 90% of tungsten, of titanium, 6% of aluminium, and 4% of vanadium. And more recently, I've been improving how to install from the source code so that it's easier. I made an importer for Abacus files, so that converts Abacus files to STL files. And I'm always working on improvement when I got the time. So I'm currently working on the deployment on a supercomputer. This is still work in progress. We can compile and we can partially run the code, but not totally. So I hope to do that, to finish that soon. Maybe by the time you hear this talk, maybe that'll be ready, hopefully. And I'm also porting the code to Vulkan, so it'd be easier to deploy on computers without a monitor. And I'm always happy to develop new functionalities if there is demand from third parties. So let's say some people might be happy with a MATLAB wrapper, but since I've done the Python wrapper, there is less demand for that. So I may not do it. I may still do it. It depends on what people like. It's been used on various applications. So there is a university in Spain that is using it to teach particle physics to undergrad students for an online course. It's been used for virtual reality, like for simulation. As a virtual testing lab, like to design some new experiments. One research lab in Spain, again, used it to develop a new imaging modality to reduce dose exposure for patients. So basically, they do one X-ray projection instead of two for dual energies, and they simulate the second one. So obviously, there is a lower exposure in that case. And maybe one of the most advanced projects is a teaching tool for radiography to train radiographers. So it's very difficult to get access to X-ray machines, particularly with COVID. So one of our collaborators wanted a tool that he could use in the lecture so that he could demonstrate what's going on when he takes an X-ray. So you could get things wrong, on purpose to show the consequences of a mistake. Something you can't do on a real patient. Next session, the theory about X-ray simulation.